G'day viewers, in this episode we're going to talk about how we can measure hardware quality with the same technology we use to measure software quality. Surprise, surprise, I'm talking specifically about Testimation technology. Okay, so now you are asking, how on earth can we link software quality assurance to hardware quality assurance? They are two completely different animals. One lives in the virtual universe, the other lives in the real universe. So how can they be connected? Well, that's a good question. I'm glad you asked. Firstly, we need to understand that software is a manufactured product. It does not exist in nature or occur naturally. It does not grow on trees. It does not grow out of the ground. It is a man-made product. No defect exists in software that a human being did not insert. A human being had to put defects into software. They did not get placed there by angels or demons. If you can understand this concept, if you have the intellectual horsepower to grasp this key realization, then you can also understand that the same manufacturing principles which apply to hardware also apply to software. Nowadays in particular, with the existence of the internet and device connectivity, hardware and software coexist. That is, they handshake with each other. Thus, the physical and virtual universes handshake with each other. A prime example of this handshaking is computer-aided design. Nowadays, many physical objects are designed on a computer system before they are actually built. The use and availability of 3D printers are a perfect example of this. However, unfortunately, many information technology professionals struggle to grasp the concept of tried and tested manufacturing principles, largely because many of them have never worked with hardware, only software. They live in a much smaller information universe than engineers, and consequently, many information technology people simply cannot see what engineers see. My point being that if you are not a real engineer, then this video presentation probably isn't for you. If you are simply someone with an information technology background, then you should move on and return to your moderator activity on social media platforms. This video presentation is intended for formally qualified and trained university-level engineers, not self-educated software developers or short-course cybersecurity analysts. Our ancestors have been making various forms of hardware for approximately 2.6 million years, starting with stone tools. So, making things is literally in our DNA these days, after 2.6 million years of evolution. In particular, since the start of the Industrial Revolution in the 1700s, we have developed scientific tools like statistics and probability in order to predict, forecast and improve hardware resistance to failure. Okay, so where are we? Well, as I mentioned at the beginning of this presentation, we're going to talk about how we can measure hardware quality with the same technology we use to measure software quality. So let's get into it by reviewing the synopsis. There are 5 key points and 2 illustrations which summarize our video presentation going forward. The key points are: number 1, all physical systems can be modeled virtually utilizing computer-aided design systems. Number 2, we live in an information universe, and it is now understood, including at the deepest level of fundamental physics, that is, quantum physics, that everything in nature may be expressed in terms of information, hence the suitability of CAD systems. Number 3, the same Testimation technology which measures software quality also measures hardware quality. Number 4, Testimation technology measures hardware quality at t equals 0 on the design, installation, potential failure, DIPF curve. The fact that we can do this is a major step forward, so please try to keep it in mind. Number 5, Testimation technology improves hardware resistance to failure predictions. Once again, the fact that we can do this is a major step forward, so please try to keep this in mind as well. The illustration on the left-hand side depicts the structure and constitution of Testimation technology expressed in Venn diagram form. The scientific tools utilized to build the Testimation technology solution are statistical mechanics, probability theory, normalization, differential calculus, Buckingham Pi theory, multidimensional analysis, and similitude. If you are an engineer, then some or all of these tools will be familiar to you. If you are not an engineer, don't fret too much. You can find them easily on the internet. It's all standard science. What I will emphasise, because it's quite important, is that Testimation technology has been experimentally verified to greater than 98.07% accuracy. Documented evidence of this claim exists. Please reach out to us if you would like to review it. The illustration on the right hand side depicts the information universe with respect to an arbitrary product or piece of hardware expressed in Venn diagram form. You can see that the information universe contains two sets, that is, the CAD system test suite and the product test suite. The CAD system test suite contains all of the physical specifications required to build a product or piece of hardware in a virtual environment, whilst the product test suite contains all of the specifications which will be physically validated by a human being. The overlap between these two sets denotes the manufacturing confidence at the instance of assembly prior to shipping the product or piece of hardware, that is, at t=0. The large amber arrow labelled Informational Transaction Entropy depicts the growth in size of the information universe as the product or hardware leaves your hands and is shipped to the customer or installed into a larger system. Once the product or hardware leaves the quality assurance test bench and is actually being utilised, its information universe expands and the disorder of the information that the product or hardware interacts with increases. In other words, as a product or piece of hardware is installed and utilised, it wears out over time and our quality knowledge of it diminishes. Eventually, the product or hardware will catastrophically fail with regular usage, in which case, as far as we are concerned, maximal informational transaction entropy has been achieved. As you should all know, the concept of entropy is standard science. None of what we have just described should be a surprise to anyone. So, what we have just described is the informational version of the design, installation, potential failure, DIPF curve. The DIPF curve is a standard engineering tool, and that's the next thing that we're going to look at. This is the DIPF curve. It is a standard engineering illustration which communicates the resistance to failure of a piece of hardware or a system of hardware components. To avoid consuming too much of your time, we advise viewers to pause the video and study the diagram to your own satisfaction. However, for now, we would like to draw your attention to the fact that the assigned defect-free confidence at t=0 is 100%. This, of course, is a complete impossibility. To make such a statement is wishful thinking and defies the laws of physics, yet it is done community-wide. Hopefully, you heard me say that this value is assigned. It is not assumed. We can say this because assumptions are based upon reality. A value of 100% defect-free confidence at t=0 is not based upon reality. The obvious question now is, why does the community assign a value of 100% resistance to failure at t=0? In other words, why does the community assign a value of 100% defect-free confidence at t=0? If this 100% assignment was sensible, how does one explain the manufacturing and sale of factory second products? By definition, they are defective at t=0, yet they are often utilised by large corporations as customer replacements in warranty claims. A well-known international computer supplier is notorious for this practice, particularly with their monitors. Let's have a look at what Testimation technology has to say about the DIPF curve. As you can see on screen, Testimation technology expresses a measured value at t=0, for example 98.56%, 99.97%, etc., not an assigned value of 100% as appears in the standard engineering illustration. Let's now work through an example in order to demonstrate how Testimation technology generates the value of the DIPF curve at t=0. To begin with, we shall define your role in this exercise. Let's imagine that you have been engaged to certify the quality of an electric motor prior to customer shipping. Similarly, this is equivalent to certifying the electric motor prior to installation and commissioning. Therefore, the quality assurance process we will discuss now refers to the assembly of the electric motor, which is executed upstream of you. It is executed by the manufacturer and the product is delivered to you. You are not required to execute these quality assurance tests. Instead, you are required to obtain the quality assurance summary report from the manufacturer. For your information, the methodology associated with the generation of the quality assurance summary report appears on screen. Okay, let's walk through the manner in which the electric motor manufacturer may execute their quality assurance process. Please remember, this information is supplied to you. You are not required to gather this information for yourself. Step 1. Assembly. An electric motor is to be assembled according to the drawing. The quality assurance objective is to answer the following question. What will be its functionally defect-free confidence at completion of assembly? Methodology. Number 1. Define a system boundary around the assembled state of the electric motor. Number 2. Identify the number of functional processes transacting information across the system boundary. In this example, only one functional process exists. That is, electrical energy transforms into mechanical energy. Number 3. On average, each component is quality assured against 4 physical properties. 27 components are listed in this example. Hence, the number of quality assurance tests equals 108. Number 4. Compute the functionally defect-free confidence utilizing Testomation technology. Thus, if all quality assurance tests pass, then the functionally defect-free confidence equals 97.96%. Okay, let's now move on to the certification process. This is where your role takes over. To this point, an electric motor has been delivered to you for certification prior to shipping to the customer. The customer shall immediately install and commission the unit upon receipt. Your role is to execute whatever suite of relevant, appropriate and meaningful tests you require in order to certify the operational performance of the unit. Step 2. Operational performance. The quality assurance objective is to answer the following question. What will be its functionally defect-free confidence when shipped to the customer? Methodology. Number 1. 4 operational performance tests are executed, validating 3 physical characteristics each. Hence, 12 tests exist in this regime. Number 2. The total number of quality assurance tests executed by the time of shipping equals 120. Number 3. Thus, if all quality assurance tests pass, then the functionally defect-free confidence equals 98.56%. Consequently, utilizing this quality assurance information, we can adjust the dip curve we saw earlier. Therefore, incorporating the quality assurance information from previous slides, we can see that the resistance to failure on the dip curve at t equals 0 equals 98.56%. Moreover, it is important to understand that a 1.44% probability of an undetected or hidden defect exists at the time of installation. Perhaps a better way of thinking with respect to decision making may not be the principle of resistance to failure, but actually in terms of the probability of the existence of residual defects which remain undetected or hidden. Ask yourself this: would you feel comfortable knowing that a 1.44% probability exists that you have missed something? Okay, let's pull everything together for the certification document. To generate a certification document, we have travelled through a 4-step process. The first step involved gathering upstream quality assurance summary report data in order to execute a defect-free confidence measurement. The second step involved inputting the information into Testomation technology. This produced a statistical measurement of the defect-free confidence of the assembled hardware which had been delivered to you. The third step involved executing your own suite of operational performance tests, then combining your results with the information obtained from the upstream hardware supplier. Once again, you input the information into Testomation technology to obtain a statistical measurement of the hardware defect-free confidence prior to shipping or installation. The fourth step involves the generation of the certification document and its associated dip curve. Well, that's the end of this video presentation. We hope you enjoyed the journey. The key business takeaways are: number 1, we can use the same technology to measure hardware risk as we do to measure software risk, that is, cyber risk. Please refer to our YouTube channel for more information. Number 2, we have presented a quality and risk decision-making tool ideally suited to project environments and delivery. Number 3, we have presented a business development tool ideally suited to differentiate your risk measurement and management capabilities over your competitors. Number 4, we have presented a scalable solution capable of working equally well with an entire plant installation and commissioning project or a single piece of hardware. Number 5, we have presented a repeatable and consistent form of quality assurance technology for hardware and software projects.